Now, if you've watched the one before this, you're thinking, why is David showing me his face again? But it's for the people who only watch this one. So I'm David, I'm the coordinator of the Maths Learning Centre. Hi there. Okay. I'm glad I make you feel tripped out. Maths should do that. So, I've been asked to talk about the randomness and probability bit. Okay. And I was specifically directed to slide 181, which is about disjointness and independence and neither or both. And I will get there. So if at any point I have forgotten to do that, when I say, could you ask me questions, let me know. Right. Okay. So here's the idea. Statistics, as I said in the other video, is about variation. We want to know when things vary. We want to know when things, how much things vary, and what's the sort of usual things. So we're interested in when things vary and when we can consider them the same. And probability is a way of talking about how things vary. Okay? Because the things that are varying are not necessarily things that even exist yet. Okay? We have rolls on a die. And we're talking about the rolls on a die vary, but I don't have any rolls of a die yet. They're future things. And in medicine, when we do statistics, we talk about babies, right? And the babies don't even exist yet. And in quality control in business, you might talk about the fat content of your supposedly low-fat ice cream in your factory. Well, the ones that you're interested in are the ones that you send out to the shops, and they don't exist yet because you haven't made them. Okay, so we're interested in things that don't exist most of the time. But sometimes we're interested in things that do already exist, but we are incapable of measuring them. Okay, we're interested in the variation between individuals that currently exist, but we can't measure everybody. We can only measure some of them. And so we're often interested in things that vary that don't exist or that we can't measure. And so probability is a way of dealing with that. Okay. And the first way to deal with anything to do with probability is to figure out what object or objects are you proposing to measure information about. It may be that you're going to measure multiple different bits of information about individual objects. It may be that you have one piece of information that you measure. And that's a key thing to being able to do probability. Okay? So this is going to be my first example. Okay? Right. Roll die. Sweet. And record the number. Probably getting an even number. Okay, so now here's the thing. The object on which we are measuring things is a die, or any future die. Okay? And we can record what the number is. And that number on the die is technically a number, right? It goes from 1 to 6 is the possibilities. Alright, that's the thing that I'm recording about the die. Okay, that's the first sentence. The second sentence says, what is the probability of getting an even number? So if I rolled a die and I was asking, did I get an even number? Now the thing we're recording is whether I got an even number or not. So the thing that I'm actually writing down is even, yes or no. That's a picture of what I'm interested in this problem. Now, do not feel embarrassed drawing pictures in your exam. because if you get it right, then you're the one who's laughing. So it's really important to realise that even though I'm writing down a specific number, the thing I'm really interested in is a yes or no. And a certain percentage of the time the yes will happen, and a certain percentage of the time the no will happen. Even though we know, for example, that all of these are equally likely, I'm interested in that going on. So that's my first step of trying to understand things. So, well, what am I really writing down here? All right. Cool. My second example. Now, at the moment, so I need to know the object, having info written down, and I also need to know what I'm writing down. Okay, I'm going to give you another example. So, at the moment, I'm not. If I was teaching this in a lecture, I would have several, and I'd go through a whole problem. But at the moment, I'm organising it differently to try and make a point. So I'm just going to pull out the information about what is going on. I'm not figuring out the probability of getting an even number right now. I will get back to that, hopefully. Record numbers. Probability of getting the same number on both. Okay. Here we go. The object that I'm recording information about, what is it? It's a trick question. It's 2 dice. I'm not writing down information about 1 die. I'm writing information down about 2 dice. I'm writing 2 bits of information down about 2 dice. But the point is that these 2 dice have 2 bits of information written down about them. And those 2 bits of information may or may not be connected. And I want to know, are they the same? Yes or no? The point I'm trying to make here is that you need to really focus on the object that is having stuff written down about it. Every probability statement that you write down is about a single object philosophically. Even if it's about 7 dice, that group of 7 dice is one object. Okay? And that's an important thing to notice. So if you were writing down about a man and a woman who are married and whether one of them smokes or the other one smokes, it's the couple that is the object that's having statements made about it in the probability. Okay? That's the key to all of this. Alright, the next thing you need to know, I'm going to put that in a box, we need to know that. The next thing you need to know we need to know what all the possibilities are and how likely every possibility is compared to the others. Okay? Probabilities only exist because everything has a probability. The only reason why you know the probability that 1 exists on a die is because you know the probability of all the numbers. The only reason you can figure out the probability of getting 2 of the same number on 2 dice is because you know the probability of all of the combinations of numbers, of 2 numbers that come off of the dice. The only reason you know the p-value in a hypothesis test is because you know all of the, from a t-test, is because you know all of the other t's that could have happened and how likely all of them are. Probability only exists because you know everything. Okay? So it's very important, at least for me, when I'm thinking probability, to stop thinking about one event, but start thinking about all of the events and the event you're interested in compared to all of them. Okay? So you need to know all the possibilities and how likely they all are. So yeah, probability only exists because all the probabilities exist. So back to my dice. For my single die probability of even, so there's my die, I get the number on the die. So here's the thing, 1, 2, 3, 4, 5, 6, they all have the same probability. I could draw a graph of the probability. Because they all have the same probability, and I know that probabilities have to add up to 1, they must all have a sixth of the probability because they all have the same. But it's not because it's 1 out of 6, it's because it's 1 out of 6 options and I know they're all the same. That's what allows me to say the probability of any one number is a sixth. Alright, so for the even numbers, what colour is even? Lots of people have a different answer for this, I just want you to shout one out. What colour is even? I'm going to guess it's blue, right? No? Oh, okay. Most people think that that even numbers are blue or green, and that odd numbers are red or orange. Think about it one day. Some people are not capable of assigning colours to numbers, and that is just something about the way their brain works. It's very rare. If you can't assign colours to numbers, then you are a very special individual, actually. Some people actually see colours in their vision when they see numbers, and it's about 1 in 10,000 people who have synesthesia like that. If you're one of those people, then you are awesome. And it's just as rare to not be able to. So there you go. Synesthesia is fabulous. Some people hear colours when they hear sounds when they see colours. So I had a friend in my education degree who couldn't sit in a lecture theatre like this because the brown was too loud. So anyway, so now when I say what's the probability of being even, I look at what even is. Even is those three. So this one is yes, yes for even, yes for even, yes for even. This is no for even, no for even, no for even. And I could, if I wanted to, I don't have to do this, but I could, if I wanted to, create a new graph which has that. Half of the probability is sitting on the odd ones, and half of the probability is sitting on the even ones. Okay, that's the picture in my head. Now, most lecturers, when they ask you what's probably being even, would not even require you to show working. You just say, well, half of the numbers are all even, so ta-da. If anything, they would probably ask you to say, well, 3 out of the 6 options are even, and therefore the probability is 3 out of 6. Okay, the only reason I can do that calculation back there is because I knew that everything had the same probability. I knew that they were all the same, and so therefore I was able to go 3 out of 6. Sweet, they're all the same. Two dice, probably if it was being the same. I've got my 2 dice. Okay, just redrawing that picture I had before. So that combination of the number on the first and the number on the second, there's a whole lot of different combinations. I could have 1 and 2, 1 and 1, and 1 and 2, and 1 and 3, and 1 and 4, and 4 and 1, because even if I can't tell the dice apart, the dice can tell the dice apart. Okay, that's an important thing to realise. Even if I don't know which die is which, the universe knows which die is which. I just don't have as good perception as other people. And so it's important for you to know that 1 on the first and 2 on the second is different from 2 on the first and 1 on the second. And so I need to think about what all of the possibilities could be. And that's what I'm talking about at the moment. I'm thinking about what all the possibilities are. So all the possibilities are, 1 and 1, 1 and 2, 1 and 3, and so on, right? And then 2 and 1 and 2 and 2, 2 and 3, and there'll be like a heap of them. I can create a table of all of the possibilities. Now, if I think carefully, it should seem reasonable that every possible pair there has the same chances as every other possible pair. And that's something that sometimes can give you a trick, but if the dice are independent of each other, if I roll a 1 on 1 and it doesn't affect what happens on the second one, I can roll a 1, that happens a sixth of the time, and then out of those sixth of the time, a sixth of those gives me the other numbers. Okay, so every one of them should be a sixth of the total, so a 36th of the total. So there's 36 options and they all have equal probability. That's the first step. The next question is to ask ourselves, well, we want to turn this into a new variable, which is whether they're the same or different. Well, same would be this bit here. So, being the same is 6 out of the 36, and being different is 30 out of the 36. So probability of same. Okay? But if I really wanted to, I don't have to draw this graph, but I would say, that's the probability graph for same or different for my two dice. Okay, it's much more likely to be different than it is to be the same. Right. Doing well. So, that allows me to get to some other stuff. Before I move on from that, be aware that some variables have nice little discrete separate blocks for each option, and some variables have many different things that they could be. Okay? Maybe not height. So a weight of a 200 gram in inverted commas block of chocolate. They're not all going to be exactly 200 grams. And the thing is that there's all these different options for what it could be. So I have my block of chocolate. And it has a weight. And my question is, what are all the possibilities and how likely is each possibility? Okay, technically to get exactly 200.10357 grams is going to be damn near impossible. But I can talk about the chances being between 200 and 201 grams. And I can talk about some of them being more likely than others. And so, instead of us being able to draw little boxes around each zone, around each specific number, I can just draw a height to tell me how likely it is to be near that number. And that's when we get stuff like this. Something like that. Okay? And this is called a probability distribution. What I drew before was a probability distribution as well. See, this is a distribution. This is the distribution of same versus different. Each of them has a probability, and the probabilities are distributed according to, there's way more of these different ones than there are of the same ones. Okay? Whereas this distribution is saying, well, my probability is distributed smoothly And it's way more likely to be near 200 grams than it is to be near something over here. That's what that's about. But it's still indicating a probability. And areas on that diagram correspond to probabilities. So half the area is here, so it's 50% of the time it'll be under 200. So it's still, though, a list of all of the things that could have happened and how likely they all are. Okay, just pointing out that that's a thing that could happen. I think I'm doing all right. Okay, just going to have a quick look at independence. Yeah. So, the thing that makes probability tricky is that you may record multiple things about the same object. And those multiple things might be related to each other. That's when probability gets harder. They're just asking, how likely is it to get a 7 or how likely is it to get above 10 when you roll 2 dice. Once you get the idea of drawing the little table, you can figure it out. But the problem is that you might have 2 different things measured on the same object, and you're interested in how those 2 things are related to each other. And that's when probability can get a bit tricky. Okay? All right. Okay, now here's the thing. Every event that you write down is actually a yes or no variable. It says either the event happens, yes, or the event doesn't happen, no. And so when you have 2 events simultaneously, you're asking yourself, are they both yes or both no, or one of them's yes and the other one's no, or one of them's no and the other one's yes? Okay? So, right. Now I'm going to do this example. A is, you get an even number, and B is less than 4. Okay? Sweet. Now let's draw our picture. The object under study is a single die, and I write down the number rolled, which has 6 options, and then I write down 2 things. A, which means it's even, yes or no. And I could also write down B, which means less than 4, yes or no. So any given thing that I could roll could be categorized into 2 of these variables. All right, so let me just draw it out. So, A is being even. So this is not A. Do you put a C for not, or do you put a bar on top? Or do you just use the word not? No, a C, okay. C for complement. Complement, which is E, which means that they add together in some way. So this is not A, this is A, this is not A, this is A, this is not A, this is A. And B is being less than 4, so these are all part of B, and these are part of not B. So what I'm doing is every option for the number corresponds to different options for the A and B. So if I rolled a 1, then this is what the A and B are. Okay, the yeses and the nos. So back here, this is what I'll call A and not A, and B and not C. And so I ask myself, I could ask various things. I could ask what's the probability of B? And 3 out of the 6 options are B. Okay? I could ask myself What's the probability of having both A and B at the same time? So A and B at the same time, that's this one, that's the only one. There's only one that is A and B at the same time, it's that one there. So 1 out of the 6 equally likely options is A and B. B, A or B would be saying, well, it could be A, it could be B. This one's got a B, this one's got a B, this one's got a B, this one's got an A, this one's got an A. That's the only one that's not A or B. Okay? So you just look for which ones have both. And so this is 5 out of 6. So just they're things that we could calculate. I'm going to draw a different picture of that just so that you can see what's going on. Just drawing all of the numbers. A is this bit. And B is this bit. So A and B is the bit that they share. That's A and B. And A or B is everything that they include either of them. So A or B there. So if you want to think of it as joining together blobs, when you join the blobs together, it's A or B. And when you overlap the blobs to get the bit where they overlap, that's A and B. Okay. Now, here's the bit where it gets really tricky. Sometimes we only care about a particular event. We don't care about what all the possibilities are. We only care about a particular selection of the possibilities. And so we're going to be focusing on just a particular part of our picture and not the whole thing. And that's what the given symbol is for. A given B is the probability that A happens. So given that you already know that B is there. Okay? And I like to think of it as the probability of A out of B. So don't say this one. You can think this one, but don't say it. A out of B. So if I wanted the probability of A out of B, that means the even ones out of the ones that are less than 4. So here are the ones that are less than 4. The even ones out of the ones that are less than 4 is 1 out of the 3. So just out of the ones less than 4, there's only one even number, 1 out of 3. 1 even out of 3 less than 4, which is 1 out of 3. 1 even out of 3 that are less than 4, which is 1 out of 3. That's what the given is about. It's about things being out of other things. You restrict your attention to just some of the possibilities, and you just do it from there. Now this is great if you can count the individual objects, individual possibilities, and all possibilities have the same probability. But you can get this via a different formula. Okay, I just haven't finished it, but probability of A given B, it's probability of A out of B, so the probability of A out of the probability of B, the same as you would do when you figure out a percentage in a test. You know, if I got 4 out of 50, that you'd do the division and it would come out to whatever percent. Okay, it's the same idea. This is the score you got, this is what it's out of. But the thing is, you can't just look at all of the A's because not all of them belong within the B. You only have to pick out the ones that actually are part of B. It's not like I said, well, there's 3 evens out of 3 less than 4. Well, that's not true. I had to just pick the ones that were within the orange circle. So it's just the ones that belong in that area. So it's just the A and B's. So it's just the A's that are in the B out of the B. The concept is, if I'm going to draw it as a Venn diagram, I don't like drawing Venn diagrams as circles because A, I can't draw circles, and B, it helps me remember that they don't have to be the same size because there could be way more B's than there are A's. So maybe this is the A's and this is the B's. The idea of A given B is that when I'm doing ordinary probabilities, this rectangle here represents all of the things that could possibly happen. But when I'm doing it just given B, I don't care about all those things, I just want to look at this bit. And so normally the big area of all the things that could possibly happen, that's 100%. But what I want to do is I want to make it so that this bit is 100% of what I'm thinking about. So to make something into 1, you should divide by itself. If I want a 5 and I want it to be out of 5, I divide by 5. So that's why I divide by probability of B so that it becomes worth 100%. And so I'm actually, what I'm doing is I'm restricting my attention. Don't want any of this crap. And I just want to look at this bit here. And this is the A's here out of the B's. So just the bit where the A overlaps B, out of the B's. Right, that's my picture. So, if I was going to ask myself, right, so there are a few terminologies that go with probabilities that are important to know because people keep talking about them, and they are disjoint, which in some places is called mutually exclusive. If you ever want to look that up online, they may not use the word disjoint, they may use the phrase mutually exclusive. So disjoint means that the events cannot happen together. It is not possible for them to happen at the same time. The word disjoint means separated. Okay? They can only happen separately. They can't happen together. That's what disjoint means. Which means that the probability of them happening together is 0. That's what disjoint means. They cannot happen together. So, is being even and being less than 4, is that disjoint? No, because it's possible for them to happen together. It's possible to be both even and less than 4 at the same time, and so therefore they're not disjoint. And you can get it here, the probability of A and B is a 6, it's not 0. So it's not disjoint. It's very important to forge this connection in your mind. Anytime it's possible for it to happen together, it's disjoint. Can you think of some things that would be disjoint out of, rolling a die? It's a tricky one. I can think of one with 2 dice. 2 dice being the same and adding up to 7 are disjoint. It's not possible to have 2 of the same number and add up to 7 at the same time. Because if you've got 2 of the same number, you have to add up to an even number. Okay, and with this one, maybe, I don't know, being less than 6... being more than 5 and being odd. That's a bit stupid because being more than 5 is being 6, which is being... But the point is that if you can say 2 statements that don't make sense together, then they're disjoint. You know, they can't happen at the same time. Be careful with making sense together, because sometimes they'll give you random crap that is just, you know, made up stuff, and it might. So do the probabilities and see what happens. All right, the other thing that you can say, and the worst part about this is that you learn about these 2 terminologies at the same time, and so you get them confused. Just like me and my twin brother, when they introduce us, they say, this is Paul and David. But they do not say which of us is which, and so nobody knows. And even if they say, this is Paul and this is David, in people's minds it's like David and Paul. Paul and David. They are twins. I don't need to distinguish which one is which. And so, even though we don't look the same, people still don't know which one of us, which name goes to which person. Same deal. You learn 2 things together, disjoint and the other terminology is independent. Psychologically, it's easy to connect them together because it's like learning the names of twins. Okay? But they are very different, and the key is to connect it to something else. The worst thing is that independent sounds like it means that they're separate from each other. But that's not what it means at all. From a statistical point of view, independent means that knowing about one tells you nothing about the other one. Okay? There is no relationship between their probabilities, between whether they happen or not. So, no relationship okay? And I think that might be the easiest way to connect it, because disjoint events do have a relationship between whether they happen or not. Disjoint events cannot happen together, so that's the relationship. So they're not independent. Disjoint events cannot be independent. They are the worst kind of dependent. Okay, if you know, if A and B are independent, are disjoint, and you know that A has happened, then you automatically know that B hasn't happened, because they can't happen together. So there's a relationship there. Knowing about one tells you about the other. So in this one, you know that being even and being less than 4 are not independent. Because if you know that you're even, if you know that you're less than 4, then you've got a much lesser chance of being even than you would if you didn't know anything. Being less than 4 means that you've got a 1 in 3 chance of being even. But that's different from not knowing anything about being less than 4. So if I don't know anything about being less than 4, I would say the chances of being even is a half. But if I know it's less than 4, there's only 1 possibility out of 3 that does that. So the probability changes when you know more information. That means they're not independent. And the definition of independent, from a statistician's point of view, it's not good enough to just make arguments like that, to say, well, they don't seem to be related. Doesn't matter. The best thing to do is ask yourself that. Is the probability of A given B the same as the probability of A completely ignoring B? So in this example, the probability of A given B came out to a third, and the probability of just straight A was a half. They're not the same, so they're not independent. That's it. And that would be your precise argument in an exam. In this question, the probability of A given B is a third, probability of A is a half, so they're not the same, so they're not independent. And that's the deal. The hard part is remembering which of these is which. My way that I remember it is to remember what disjoint means and know that independent is the other one. So go, disjoint means they cannot happen together. Disjoint means completely separated. Sweet. Independent's the other one. You get a cheat sheet for this course, don't you? Right, so you can put statements like that. Okay, if you can find a way of saying it that makes sense to you, then it's more likely. So when I think of this thing, I actually have 4 things connected together. I have the word, I have a saying, I have a math statement, and I usually have a Venn diagram picture. The thing is that you can't draw a picture of independent because it's too hard to tell what it means from the picture. Because it's saying the picture of independent is that, you know, this out of the whole is the same as this out of here. It's like, I don't know. Okay? If you drew them carefully enough, you might be able to do it. Let's think about it. So this is the whole. And maybe this is A here out of the whole. And what I want to know is that A out of the whole is the same as A out of B. And so I can imagine that if B was the right area, then A out of B is the same as A out of the whole. Something like that. That's my concept off the top of my head. It's my first pass at attempting to draw an independence picture. I've never tried before. But it's saying that, look, this area, actually, I could do it really well if I did folding. That totally doesn't work. Sorry, it was worth a try. Okay. The idea is that the areas is that this represents maybe 10% of the area, and it also represents 10% of the smaller area. Like they're the same size relative to the thing that you're looking at. That's the idea of independence. Right. I probably should sort of stop soon unless there's any questions about that I need to do before you go, because I'm happy to keep going for a couple more minutes. Was there anything else about that area to talk about? Yeah. I find that the key, thinking through what the objects are and where they are. Yeah. Well, thank you. Do be aware Maths Learning Centre is open until the end of the exam period. Not that that's relevant for BES. Poor people with that early exam. It's a good idea to walk around and see if anyone's written BES on a little sign on the table so that we can group you together. There will be a lot of people from first year maths, but don't let that intimidate you. If you can't find space in there, feel free to sit in the space next door and run in to let us know that you're there, and we'll come and check on you. Okay? Excellent. Good luck. No, just a second. You don't need luck. You'll be good. Okay? Study, ask questions, and you won't need luck.